you to another multivariate statistics class. Of course, today we got a lot to do. So um, I'm actually going to be introducing you to linear algebra because linear algebra is very, very essential when it comes to analysis of multivariate data. But before I get started, I want to make announcement about miscellaneous material that I've already uploaded on Canvas that contains R. It is this material. So this material, I will advise that you go over that. Okay, it gives a lot of examples, and not only that, how to implement uh the focus of the week of the topic of the week in R. So they are all in this material. So how we implement that using R software is actually provided in this material. So I will advise that you go over this material. Okay, so I'm gonna go back to material for today. I call this introduction to linear algebra. Um, I said in the one that we live in a mathematical world, and if we really want to understand the world, then we need to go mathematical. Now, when you look at multivariate data set, you know, um, consists of observations that have multiple variables, the multiple variables that are related. And of course, we normally use matrices, vectors to represent multivariate data. When you are using matrices or you're using vector to represent multivariate data, of course, that is a core concept of algebra because linear algebra provide us a mathematical framework of manipulating, of generally representing complex relationship in a compact matrix form. And that is the reason why we got no choice. We actually need to understand some basic fundamentals of linear algebra. Okay, so once again, I welcome you to linear algebra. Of course, in this material, you're actually going to learn the basic definitions, vector and matrix. Don't forget I said multivariate data are represented in form of vectors and matrices. I remember uh, yesterday when I talked about vector means, I talked about covariance matrix and so on like that. So we in this course you actually need to revise your knowledge of fundamental properties of vectors and matrices. We talk about transpose, the trace, symmetric, diagonal, special matrices, and so on like that. Then we're also going to talk about matrix decomposition because if I want to talk about data reduction technique, or maybe I want to talk about image compression, or I want to perform or any of those tasks, then I need the knowledge of some of them involve decomposing matrix. And that's why you need to be able to understand, you need to revise how do we decompose matrix, the Igula, the eigenvalue decomposition, the Koleski, and so on like that. Then matrix equality, matrix addition, you know, product, and so on, like that. So, and of course, the miscellaneous topics, like I said, included in Haro code, is contained in the material that I showcased the other time. Now let's go to basic definitions. We all know why we're doing what we're doing right now, because when you have a multivariate data set, multivariate data set, we always use matrix and vector to represent them. And the moment we use matrix and vector to represent them, then it means we can actually seek redress using linear algebra. Okay, and that is the reason why right now we actually want to familiar ourselves with how do we actually go by way how do I mean, matrix algebra. So we need to understand some basic fundamental principle. Now, this is a vector. A vector can be a column vector, it can be a row vector. We use that most of the time when we are defining means across a variable. So we can use column vector or mean vector or row vector for that. And of course, if you look at matrix A, okay, so that is matrix A, that is the typical of how our data frame in multivariate analysis normally look like. Okay, so the vector is n by 1, and of course, the dimension of the matrix is n by p. Don't forget, the other time I said n is the number of observation, and of course, each observation, we collect, we collected so many variables on each observation. Now, we want to start by looking into the properties of matrix. Okay, that's something that we call the rank of a matrix. Okay, the rank of a matrix is the number of independent rows and independent columns. Okay, now the rank of a matrix is very, very useful when it comes to singular value decomposition. Okay, singular value decomposition, where maybe the focus is on decomposing an image. Okay, so we normally make use of this idea. But what I just want us to understand now is having an understanding of basic mathematical provision for rank. So when I have a matrix, okay, and I want to find the rank of a matrix, okay, now the rank of a matrix is actually going to be, like I said, the numbers of independent rows and the numbers of independent column. We could have a column rank, we can have a row, we can have a row rank. So having a column rank, and I said that will be the number of linearly independent columns. We want a situation where the columns are going to be they're going to be linear and they're going to be independent. Okay. So for row rank, of course, the linearly independent rows. But you know what? When I have an image, okay, if I don't want to compress an image, then the image is expected to have a full rank. Every image is a matrix. Okay, that's a dimension. Image as a dimension. Okay, so if I don't want to compress it, it's actually going to have a full rank. And what do we mean by a full rank? We said A is a full rank if the rank of A equal to, it has to be the minimum of the numbers of rows by the numbers of columns. The numbers of row is n. Don't forget, numbers of rows in this case is going to be number of observations, and the numbers of columns is going to be the numbers of features. So definitely the minimum of n and p. When I say minimum of n and p, if n is 10 and probably p is 5, then the rank is going to be 5. That's all it means. Okay? So minimum of that. Now, but we want to consider situation because depending on the nature of the data set that we have, okay, I needed to pay attention to this guy. Give me 1 second. Pay attention to this guy. Okay, situation where the number of observation is less than the numbers of features. Okay, what does full rank implies? If it is the other way around, where the number of observation is greater than the numbers of features, what does full rank implies? Okay, so when the number of observation is less than the numbers of features, of course, the full rank implies the full row rank. Full row rank. Okay, what we mean by full row rank, don't forget, we are targeting the minimum, right? So the number is less than P, then the rank of it will be N, will be the minimum number. Now, for situation where N is greater than P, on the other hand, okay, where N is greater than P, P is going to be the minimum, then the rank of A is going to be P. Because with the rank we are targeting, the minimum. Is there any question on this page before I move to the next page? Is there any question on that? Okay, so if there's no question on that, I'm actually going to move to the next page. Now, we want to have an Iraq example now. Okay, now you have that matrix. Right now, the number of observation is 3. Can you see that? With numbers of rows is 3. How many columns do we have? How many? Can someone tell me? How many? 2. Thank you. We got 2 columns. Okay. Send me a message for extra credit. But when you want to answer my question, because at the end of the semester, I normally apply, I'm going to send message to students. I'm going to ask them how they want to spend their extra credit. So if you answer my question in class, because I believe exam starts now. Okay. So you send me a message that, okay, you answer my question and that will be 1 point. You can be accumulating the point. Okay. So if you take a look at what I have right now, the number of observation is actually greater than the numbers of P, right? The numbers of features, right? And there's something I want you to see that you need to pay attention to when we talk about rank. We actually say if I'm looking at it from a column angle, okay, the column have to be independent. But let's take a look at this. We really want to see. Let's investigate each column to see whether they are independent. Take a look at this column. Oh my God. When you take a look at that very column, it's looking like if I multiply the first column by 3, I'm going to get a second column. Therefore, there's a violation here of of independent that we talk about. Okay. And that was why I said 3A1 equal to that. Okay. Now, uh, in a situation, and that is the reason that very A is not going to have a full rank, even though it's going to have a rank, but it's not going to have a full rank. The condition for it to have a full rank, we expect situation where there's no connection between the columns or between the rows. Is there any question on that? Now, but if that doesn't happen, then it's going to have a full rank. And that is why here I said, because we cannot write the summation BA to be 0, 0, 0, okay? Because that is the condition under which they actually going to have a full rank. Okay, now I'm going to move to the next slide. Now, on this slide, we actually want to transform matrix, we want to manipulate. Let me tell you this. The only way we can get a meaningful information from data set is to manipulate data sets. And one of the way to manipulate data set, particularly when you're working with matrix, is to want to find the transpose of a matrix. So now if I have I can find the transpose of a matrix, I can find the transpose of a vector. If I have if I have a vector, is a column, I find the transpose, that's going to give me a row vector. Okay, transpose is converting column to row or row to column. That's all. Now for the matrix, I have a matrix A, and I want to find I have to find the transpose. Please pay attention. This is in notation. You can see here I put you can see something on A. So that's a transpose of A. So the transpose of A now. So what's going to happen, okay, is we basically converting the element, here it's occupying row and here it's now occupying column. Okay, that's just the idea. But we don't know why, we don't know the reason why we're doing this right now. Okay, by the time you get to multivariate regression, Of course, where you want to optimally estimate the regression parameters, you're actually going to see that we're going to perform this kind of operation. But right now, let's prepare our mind mathematically. You know what we're doing now? We want to incube our mathematical knowledge, okay, of how do we do transpose, how do we manipulate data set, and so on like that. Okay, so that's what we mean by transpose. And of course, when you find the transpose, the dimension is going to change. Initially, it was n by p. After finding the transpose, it's going to be p by n. Okay, okay. Now, if there's no question on that, I'm actually going to move. And this is an example that I'm giving here. You can see I have a column vector 1759. I'm finding the transpose of that. That gives that initially. It was 4 by 1. And after taking the transpose, I get 1 by 4. Then look at a matrix there. After of finding the transpose, that's what I have. But right now, just like the same question my daughter used to ask, why are we doing this? You don't know why we're doing this now. We're just changing position. But by the time we go into application, you're going to see us applying this. Okay? But right now, we just want to refresh our memory, okay, of matrix algebra. There's no question I'm going to move forward. Now, because of what we've done, we want to go to some properties of transpose. Okay. Now, when I have a transpose, when I do transpose twice, it will return me back to the original matrix. That's what the first one is trying to talk about. Transpose of a transpose. And maybe I convert row to column and I convert column back to row. Then it's like it has returned back to its original space. So that is what the first talking about. The second one, if I have two matrices, I add them up. When I find the transpose of the addition, it is the same as adding the transpose of each matrix. We can investigate all of that. Okay. Now, if you look at the third one, I have a constant b. At times we use constant to multiply matrix. Okay. Now, if I multiply a constant by matrix and I find the transpose, it is the same thing as multiplying the constant by the transpose of the matrix. So that is what that guy is trying to say. And when I find the transpose of the product of a matrix multiplication, okay, then it is the same thing as that. And let me say this. When I find the transpose of an inverse, okay, another properties of matrix is inverse of a matrix, very crucial in regression modeling. Okay. Now, if I find the transpose of an inverse, it is the same thing as finding the inverse of the transpose. That is what this guy is trying to talk about. Finding the transpose of an inverse is the same thing as finding the inverse of the transpose. Okay. Now, those are the properties. Now I want to move right now to trace, metric trace. This is very, very useful by the time we start singular value decomposition, where the focus may be on the diagonal of a matrix. And let me tell you this, by trace of a matrix, the trace of a matrix has to do with adding elements in the diagonal. Okay, when I say diagonal, give me 1 second. This is what I mean. Please pay attention. Okay, that's what I mean. Okay, that's what we mean by trace. Okay, adding all the elements in the diagonal. That's what we mean by trace. Okay, by the time when we start principal component analysis, okay, and you actually have what I call uh, the covariance matrix, of course, in the diagonal will be variances, and of course, in principal component analysis, the interest is on total variance. So to the total variance is just adding all the diagonal, okay, the elements in the diagonal. So it's just the sum of the diagonal elements. So that's what we mean by trace. Okay, it's an example. You can see with the way I'm doing it. Okay, I gave you the theory, I gave you the example, and how to go about it. And of course, if you check the material that I showed you the other time, there is coding out on how to go about this in case you have uh, you know complicated data set. Now, I have a matrix of this nature, and I want to figure out the trace of the matrix. So just adding the element in the diagonal of the matrix. Okay, so this is the diagonal of the matrix. Can you see that? So I'm just going to add them up. So that's exactly what I'm doing here. Okay, the trace of that matrix now is actually 18. Okay, so that's 18. Okay, now I'm going to move right now. We're still on linear algebra. It's an introduction to linear algebra. Now, we also have properties associated with trace. I remember the other time, I show you properties associated with transpose. We also have the one for trace. Okay, so if I have a matrix A and I find the transpose of the matrix A, okay, if when I do the trace for the two will be the same. The trace of original matrix A and the trace of the transpose of that matrix, the trace is going to be the same. Okay, so when you try to change, change element in the row and element in the column, the one in the diagonal, is still going to the addition of the one in diagonal is still going to stay the same. Okay, so the trace of addition of the two matrices is actually equal to the sum of the trace of the individual. And of course, if I have a b, if I, lowercase b here, it's actually a constant, and I multiply it by a matrix. Okay, if I multiply, give me 1 second, let me see if I can use, okay. Now, if I actually multiply b, okay, which is a constant, by a matrix, and I find the trace. Okay, it is same thing as I can first find the trace of the matrix, and after which I'm going to multiply by the constant. So you can try that. Okay, then the trace of AB, if I have matrix A and matrix B, after multiplying them together and I find the trace, okay, it's going to be the same thing as finding the trace of BA. But don't forget, AB is not equal to B because multiplication is not, if I multiply A by B and multiply B by A, okay, it's not commutative. It's not going to give the same result, but the trace will be the same. That's exactly what we're talking about. Okay, another thing is if A is symmetric, okay, when we talk about A being symmetric, maybe you're trying to find the transpose of A also is the same thing as A, and you find the trace of that. The trace is going to be the sum of the lambda. Okay, by the time we start principal component analysis, of course, you're going to hear something that we call eigenvalues. The eigenvalues, they actually going to be the elements in the diagonal. Okay, so that we actually interested in. Okay, so I'm actually gonna move. Okay, so by symmetric, of course, uh, when if I find the transpose of a matrix and it is equal to the original matrix, then that matrix is said to be symmetric. A very good example of that is covariance matrix. Okay, covariance matrix is gonna be a very, very good example of a symmetric matrix. That's what I mean. That's what we mean. Okay, there's an example. Okay, I have a matrix A, 4 by 4. Okay, and if you find the transpose of it and is given the other one, then we're going to say, but it is not all matrices that are symmetric, because if you take a look at this one now, okay, when you find the transpose of that, okay, what we're getting, okay, you can say the matrix A is that, and you find the transpose if you take a look at this, for instance, take a look at the first one. If you make an attempt to find the transpose of that, because this guy is the same as this guy. Can you see that? 9104. So if you find the transpose of that, it's going to be the same as this matrix. But if you make an attempt to do the second one, you can try it. If you make an attempt to do this one, the fact that this guy is not the same as this guy, it's not going to be symmetric. Why is it not the same? The other guy at the row is 9104, and the one at the column is 9103. They're never going to be the same. Does that make sense? Is there any question here? Before moving forward, let me tell you this. To have an excellent grade in multivariate analysis requires you having a mathematical knowledge, that is, the algebraic knowledge, okay, and how to use software, okay. So, and that's why I'm walking you through refreshing your mathematical knowledge, particularly matrix algebra. Okay, then we also have diagonal matrix. I think I'm going to move so fast now. So we have diagonal matrix. A matrix is going to be diagonal if off diagonal is going to be 0, 0, 0, off diagonal. When I say diagonal, so what do I mean by diagonal? Take a look at this guy. Okay, that's what I mean by diagonal. So off diagonal have to be zeros before I can call it a diagonal matrix. Any question? And here, uh, we want it to be, this is going to be a square matrix. That's why you have P by P. Okay, square matrix, numbers of rows and columns, they're going to be the same. At times, the focus may be on the diagonal matrix. Okay, now the next one, identity matrix. Okay. Now, when you talk about identity matrix to me is a special form of a diagonal matrix. But the difference between identity matrix and the diagonal matrix is that in identity matrix, the values in the diagonal has to be 1, 1, 1, 1. But for the diagonal matrix, of course, we could have, it's going to be a combination of one and some other numbers. But the similarity between identity and the diagonal matrix is that they are off diagonal have to be zeros. Is there any question on this before moving forward? Okay. In case you don't understand, please ask questions. Now I'm going to move right now. Now, and I also need you to pay attention to notation. Okay. High P means, okay, that's our identity, okay, and of a P by P dimension. Okay, so take a look at that. Okay. Now I'm gonna move right now. Now zeros and one matrices. Okay. We could have a zero vector. How? Oh, we could have situation where the means of features is 0, 0, 0, 0. Okay. And we could have situation. Oh, that would be a special situation. I remember yesterday when I was walking you through the distance between random variable and origin. Okay. So now take a look at all of this 0, 0, 0, 0, 0. Can you see that? And we also have a matrix of 1, 1, 1, 1, 1. Okay. Also very crucial. Okay. We just wanted to, but right now you may not know why we have this, but we're just trying to say there's possibility of having this. Okay. Now to basic calculation. Okay. To basic calculation now. Make sure you revise the knowledge of, you know, matrix equality. Okay. So what do we mean by matrix equality? Okay. Maybe you have like two different set of data set. Okay. and you realize that this data frame is just exactly the same as the other data frame. Exactly. All numbers stay the same. Numbers in a corresponding position the same. One here. Okay. 4 here, 4 here. All entries, they stay the same. And that's why equal to B. But you know what? Even if most of them are the same and there's a violation, take a look at that. This is 9 here and this is 0 here. Even if every other number stay the same, then I'm actually going to say the two matrices are not the same. So for them to be equal, all numbers, all entries in the corresponding position have to be the same. That's what I mean by matrix equality. Now, we can talk about matrix addition and matrix subtraction. Okay, adding two matrices together and subtracting matrices. I will advise that you actually revise that. This is an example. I have matrix A, I have a matrix B. Okay, and you know what? This is adding matrices together. Adding them together requires that they have to be in the same dimension before I can add them up. Before I can subtract, they also have to be in the same dimension. Is there any question about this example? Okay. Now, make sure you revise that. We need them in multivariate analysis. Now, the next is vector inner products. This is very useful in regression analysis. In regression analysis, we are maybe I will feed a model. How many of you have seen regression model before? Okay, thank you so much. Okay, good number of you. Okay, so if I have y equal x beta plus the error, okay, we are talking about multiple linear regression model, okay, and I want to figure out, okay, the beta now. Okay, I want to provide the OLS estimate of that in the formula. You're actually gonna see you're gonna see all of that. Oh my God, what am I saying right now? Without the knowledge of matrix, there's no way we'll be able to obtain the regression estimate, provide an estimation for regression parameters. Take a look at that. Transpose, you can see a transpose, you can see inverse, you can see a transpose. Now, when I talk about inner products, okay, I want to focus on this guy, S prime Y. Okay, now I got you take a look at that. I have a matrix X. Okay, in transpose, I have a matrix Y. I can multiply S transpose by Y. That's what I'm doing here. Oh, okay, and that is going to lead us to summation of XY because you know what I'm going to have. Okay, if you take a look at what I'm having now, so S1 multiplied by Y1, S2 multiplied by Y2 until I get to xn multiplied by yn, and I'm going to add them up. Okay, and that's why you have this as a general formula. Okay, so what a guy is trying to say, okay, so what a guy is trying to say is, if I have, I want to do X transpose Y, and of course I know X1, S2 until I get to Xn, okay, and I have Y1, Y2 until I get to Yn, okay, this multiply by that multiply by that until you get to that multiply by that. I'm actually going to have this guy S2, Y2, so until I get to Xn, Yn, and of course, in a general form, then I'm actually going to write summation Si, Yi, I start from 1 to n. So this is X prime Y. This is in matrix form. Okay. This is in matrix form. Okay. Why this guy is in scalar form? That is in scalar form. Okay. That's what we mean by inner products. That's what we mean by inner products. Any question? Go ahead. Okay. Um, Actually, even though the two are are in the transpose position, uh, we actually not going to say S prime times Y prime because we have to obey the condition that will make them conformable for multiplication. So the very good idea is okay. I'm only going to use x prime to multiply y because the number of columns in this one, the number of column is this have to be equal to the numbers of row in the other one. And that is why it has to be x prime y and not x prime y prime. Because if I'm going to do x prime y prime, I don't think it's going to be conformable if I use this one in the row form to multiply the row form. I don't think it's going to be conformable. But when we talk about inner product, okay, inner product means we're using a transpose of one matrix to multiply not the transpose of the other, the original of the other variable. So that's why. And which is going to provide the basis for one of the methods we use in statistical modeling. And I want to believe you've seen summation XY before, right? Okay. Without this, we're not going to have summation XY. Yeah, because we have to, there's a rule for matrix multiplication. So the rule is if I want to use this matrix to multiply this matrix, the numbers of columns here have to be equal to numbers of rows. No, X is a row vector here. The X prime here, can you see? Can you see X prime? You can see here it is a row. But Y is a column vector. What do you mean by yeah? All the variables are column vector. All variables. You remember features? They are column. It now depends on what you want to do with them. So if I want to do matrix multiplication, maybe operation on that, then I just have to ensure that they are conformable for multiplication. That's all. Does that make sense? So the moment we ensure the conformability, we're good. Yeah. Okay. Now, and the scalar vector is always going to, when I say scalar, no matrix anymore. Just one by one, like one figure, one answer. Okay. One value. Okay. Now, there's an example that's going to be one value, 7. So this is a way of, performing a matrix multiplication here is to arrive at a particular scalar value that we may need in multivariate analysis. Is there any question with that, with what we have right now? Now, let me tell you this. If I want to know whether I should use S prime Y or whatever, now this one, how many rows? This is 1 by 4. Okay. This is 1 by 4. But this guy is 4. Is 4 by 1. Okay. Now, if I want to know whether they are conformable for multiplication, okay, if I want to know whether they are conformable for multiplication, this is row, this is column, right? This is row, this is column. And the law of matrix multiplication implies the numbers of column must be equal to the numbers of row. The numbers of column of the one I want to use to multiply must be equal to the numbers of row. And if that happens, they are conformable for multiplication. How am I going to know the result? The result is going to be this guy. The result is going to be this. What is the result? 1 by 1. At the end of the day, 1 by 1, which is just this guy, scalar. That makes sense? Okay. Now I'm going to move right now. I'm going to move right now to the next slide. Now, going to the next slide. Now, in this case, we talk about vector outer products. What is the difference? Oh, the other time, what I used to multiply was a transpose. Okay, I'm going to go back. I wanted to see the difference. We call that one here. Take a look at this. Vector inner product. What I'm using to multiply has to be transpose. But in the case of the outer now, okay, the reverse is going to be the case. What happened? I'm using S to multiply by the transpose Y. And if I investigate again, okay, in this case, I want to see whether they are conformable for multiplication. Okay, what is the dimension of X of this column matrix here? Okay, it's actually M, M by 1. Okay, this is M by 1. How do I know? X1 to XM. Okay, and this guy. Okay, if you take a look at this guy, okay, how many rows do we have? So this is 1 by n, right? Now the number of column equal to number of row. Can you see that? What would be the final result? M by n. That's why this is M by n. You know, before you do matrix multiplication, you have to investigate if they are conformable for multiplication. Okay, and what is the investigation here? It's going to be is the number of columns of what I want of a matrix I want to use to multiply, okay, the order equal to the numbers of the row of the order. And that's all. So that's why. So this is defined. Okay, now I'm going to move right now. So far, so good, everybody, right? So far, so good. Okay, let's keep moving. Now, this is an example. You can try this out. Okay, this is an example. Okay, you can try that out. Now, we want to move into matrix scalar products. Matrix scalar product means scalar is a constant. It's like I have a constant. I want to use it to multiply a matrix. Here is a matrix. A lowercase b is a constant. Then you're gonna see the constant in every of the element because it's a constant. Okay, so take a look at that. It's very easy to do. The multiplication with matrix and a constant is very easy to do. It's an example. I have a matrix A and a constant B equal to 2. What I'm just going to do is to multiply every element occupying every position by the constant. And at the end of the day, that's what I got. Any question? Okay. Now we want to keep moving. Now we want to talk about matrix vector products. What do I mean by that? Matrix, vector, product. I'm using matrix to multiply vector. Okay? I have a matrix A. I have a vector X. Then I can do AS provided they are conformable for multiplication. Okay? And at the end of the day, this is what I have. This is what I'm going to have. Okay? This is what I'm going to have. Okay? Then I'm going to move. It's an example of a matrix vector. I got a matrix and I got a vector. Then I want to multiply it by X. Okay? And you see the way it is done. I'm still going to, if I want to do that, I'm going to go from row to column, from row here to column. Okay? And if I want to do that, 3 we go for 1, 4 we go for 6, 1 we go for 3. So I'm multiplying them, I'm going to add them up. That's what I'm doing here. Okay, then it's going to be the turn of the second row. I'm going to do the same. Okay, 4 go for 1, 7 go for 5, 4 go for 6, and 5 go for 3. That's what I'm doing here. At the end of the day, I have my answer. Take a look at that. Beautiful. Can you see that? Right now, we're just doing maths. But you know what? Probably from next week, by the time we start application, then you will start appreciating why we're doing what we're doing right now. Okay, the problem we have in the world is with the problem of math. The moment we understand the mathematics, okay, every other thing is going to be easy. What is mathematical in nature? Okay. Now let's keep moving. Right now, we want to go into another one. This time around, matrix products. We talk about matrix vector product, but right now, matrix product. You're actually going to come across all of this, and when we're dealing with decomposition of matrix. For instance, maybe we want to talk about um, uh, principal component analysis, the factor analysis, um, document word matrix, and so on like that. You're actually going to come across stuff like this. But you know what? What we're doing right now, we're preparing our mind mathematically. We want to be ready. Okay, we want to be ready. I used to tell a student in statistics, doing masters or doing PhD. If you're doing masters or PhD in statistics, and if you have issue with it, then you have issue with maths. So you have issue with maths. So the moment you understand mathematics very well, your statistics is going to be so easy. Okay. Now I have a matrix A with dimension n by n. Now I have a matrix B with dimension n by p. Take a look at that. If I investigate their conformability for multiplication, I can multiply them. Okay, that's what I'm going to have. But you have to take note that AB may not necessarily be equal to BA. Okay, so that is what I'm talking, that's what I'm talking about there. Okay, this is an example of matrix, multiplying two matrices. Okay, and this is what we have. If I were you, why can't you, you know, take some example, work on that, So that's an example. Then multiplying by identity matrix. Let me tell you this. When I say, when you talk about identity, I think I'm going to say something about identity. If I want to preserve, I remember in pipeline software or in neural network in general, where we want to preserve the values of an input. That's not identity. Identity actually means, okay, input is the same as output. F of S is the same as S. Okay, that's what we call identity. Okay, and let me tell you this: in medical diagnosis, identity is very, very crucial. If a response, okay, from a medical field is identity, then that indicates a normal healthy individual, a normal healthy state, okay, which you're actually going to use it as a comparison, okay. If you have a patient, you want to treat a patient as a doctor, you want to return the state of that patient to normal states. If a doctor work with somebody that is not sick, okay, at the end of the day, what is going to happen? The person is not going to be sick. F of 4 equal to 4. So in matrix, when I multiply identity by a matrix and it give back, if I multiply something by a matrix and we have the matrix back, then what we have used to multiply that matrix and identity is going to preserve it. It's not going to change it. Okay, that's what we mean. Okay. Oh my God. That is going to be the end of, that's all what I got for you today. Okay. Like I said, I advise that you should take um linear algebra very, very seriously because the problem statistics student may have with analyzing multivariate data set is actually going to be the problem of algebra because algebraic knowledge is very, very crucial if you really want to bring out a meaningful information from multivariate data set. Does that make sense? But what we did today, we have a recap on matrix algebra. But by the time we go into real analysis, the real application, then you're going to start seeing us, okay, applying the transpose, applying this, applying that. Is there any question before I go today? Is there any question? Like I said, do not hide your feeling. Now, this is what I want us to be doing. If it is possible, I want to hear a feedback from you. Now, I need you to rate your understanding of a particular topic, like today's topic, for instance. Rate your understanding, okay? Rate your understanding, okay? Rate your understanding from 0 to 100%. For instance, if you understand what I've done by 80%, then I need you to include in your message what you don't, what you are struggling with. Then I'm going to reply. That makes sense? Summer semester is very, very short. And of course, uh, because the moment somebody is struggling in day one, there's possibility the struggle may continue because topics are connected. So I want to hear from you. Feedback actually work. Is there any question before I go today? Any question? Okay, go ahead. Exactly. Exactly. So like um since I'm starting today, okay, you can give me your you can rate your understanding for today. And the work you've done before, rate your understanding too. So that from tomorrow, when we do another one, then you rate your understanding for tomorrow. You get what I mean? But since I'm starting today, so if you want to rate your understanding, you have to rate your understanding for what we've done from Monday and today. So you're going to do it one at a time, okay? So you can include that in the same message. And if your understanding is less than 100 in each case, tell me, okay? Tell me what you're not getting. Maybe something you need clarification on. Then I'm just going to reply you, okay? Okay, blah blah blah. This so because feedback helps me a lot. When I hear from students, it's going to help me a lot. Because my joy, what's going to be my joy at the end of the day is if everybody in this class has an A, which is possible. Okay? I think you get that right. Okay, make sure you stay safe. I'll see you tomorrow. Bye for now, everyone.